You have never once doubted that the world is still there when you stop looking at it. You leave a room and trust that it stays exactly as you left it. You close your eyes and assume the moon is still hanging over the house. But here is what they never told you. For more than 100 years, in the quietest experiments ever performed, the smallest pieces of the world have refused to behave like things that are simply already there. A single particle, fired alone, passes through two openings at once. The instant a machine records which way it went, that behavior vanishes, even though nothing ever touched it. And when physicists finally tested whether reality is definite before anyone looks, they proved the comfortable answer wrong. The world you assume is already there cannot be real in the way you picture it. So tonight we sit with the strangest question in all of physics, the one no one has answered. What happens when no one looks? Get comfortable and settle in. Hit subscribe if you are new here, because by the end of this, the solid world you have always trusted will feel far stranger and far more wondrous. Now, let's slowly ease into this. Part 1. The world you think is already there. Right now, without thinking about it, you are trusting something enormous. You are trusting that the room around you is there. You trust that the walls are holding their shape even when your eyes are closed, that the floor stays solid underneath you whether or not you are looking down at it, and that the ceiling has not quietly stopped existing while your attention was somewhere else. You trust that the moon is hanging in the sky tonight, even though, at this exact moment, you are almost certainly not looking at it. You assume it is up there, fully formed, complete, patient, in case you ever decide to glance up and check. This assumption sits so far down in us that it does not feel like an assumption at all. It feels like the most ordinary fact there is. The world exists on its own. Objects have properties, a position, a speed, a color, a temperature, and they hold those properties continuously, whether or not anyone is paying attention. When you look at something, you are simply finding out what was already the case. Looking reveals. Looking does not create. The cup of water on the table was at a certain temperature before you touched it, and your touching it only told you a number that was already true. Children work this out early, and then spend the rest of their lives taking it for granted. A small child wonders whether the light inside the refrigerator stays on after the door is shut. It is a surprisingly serious question, and the adult answer is reassuring. The light goes off, we say, and we are certain, because the world behaves in a consistent way whether or not we are there to see it. The milk stays cold in the dark, the shelves keep their order. Nothing waits for your eyes before it agrees to be real. Philosophers gave this comfortable belief a name. They call it realism, the idea that there is a real world out there with definite properties, and that this world does not depend on us in any way. For almost the entire history of human thought, realism was not even controversial. It was the floor everyone stood on while they argued about everything else. Isaac Newton built his physics on it. The whole machinery of science seemed to assume it. You measure the world to discover its hidden numbers, and the numbers are there waiting to be discovered, like the inside of a wrapped gift that already has a definite shape before you tear the paper. For a long time, this picture worked so well that there was no reason to doubt it. The planets moved along paths you could predict centuries in advance. Cannonballs followed curves you could calculate. Heat flowed, water froze, light bent through glass, and every single time the explanation assumed a world that was simply there, behaving by fixed rules, indifferent to whether anyone was watching. The universe was a great clockwork, ticking along on its own, and human beings were latecomers who had wandered in and started reading the dials. And then, slowly, beginning a little over a century ago, that floor began to crack. It did not crack because of some violent discovery. There was no explosion, No telescope pointed at a monster in the sky, no single dramatic announcement. The trouble came from the gentlest experiments anyone has ever performed. It came from shining a little light through a couple of narrow openings and from firing tiny particles, one at a time, at a screen. It came from setups so small and so quiet that you could run them on a tabletop in a darkened room. And what those quiet little experiments revealed was that the comfortable story we tell ourselves about reality, that it is simply out there, fully formed, whether or not anyone looks, might not be true. Not might be incomplete. Might not be true. Over the next 2 hours, we are going to walk through this together, slowly, the way you might walk through a building you have lived in your whole life, only to discover it has rooms you never noticed. We are going to start with the experiment that first made physicists uneasy, and then we are going to follow that unease as it grows, decade by decade, experiment by experiment, until it arrives at a question that the smartest people alive still cannot answer. The question is the one in the title, and I want you to hold on to it, because we will keep returning to it. What happens when no one looks? You probably think you already know the answer. Almost everyone does. The answer feels obvious. When no one looks, the world simply carries on, exactly as it would if you were looking, minus the looking. The moon stays where it is. The particle keeps its position. Reality does not need an audience. I am going to ask you to set that certainty down, gently, just for tonight, not to throw it away, but to loosen your grip on it, the way you loosen your grip on the day before you fall asleep. Because the strange thing, the thing that kept some of the greatest minds of the 20th century awake, is that when you look closely at the smallest pieces of the world does not seem to behave like something that is already there. It behaves like something that waits, and the first hint that it waits came from a single particle faced with 2 open doors, doing something that a solid, already there object should never be able to do. Part 2. The particle that goes through both doors. Imagine the simplest experiment you can picture. You have a wall with 2 narrow vertical slits cut into it, side by side, like 2 thin doorways close together. Behind that wall, farther back, you have a screen that lights up wherever something hits it. And in front of the wall, you have a source that sends things toward the slits. To begin with, imagine you are throwing tiny pebbles or firing little balls of paint. Some go through the left slit, some go through the right slit, and on the screen behind, you get 2 bright stripes, one behind each opening. This is exactly what your intuition expects. Each pebble is a solid object. It goes through one slit or the other. 2 doors, 2 piles. Nothing surprising. Now replace the pebbles with light. When you send light through 2 narrow slits, you do not get 2 stripes. You get many. You get a row of bright bands separated by dark gaps, spread out across the screen, fading as they go outward. This pattern has a name. It is called an interference pattern, and it is the unmistakable signature of waves. When water waves pass through 2 openings, they spread out on the far side as overlapping ripples. Where 2 crests meet, they add together, and you get a bigger crest. Where a crest meets a trough, they cancel, and you get flat water. Bright bands are where the light waves add. Dark bands are where they cancel. Thomas Young demonstrated this with light in 1801, and for 100 years it was taken as clean proof that light is a wave. No mystery there. Waves do wave things. The mystery begins when you make the experiment smaller and quieter than Young ever could. In the early 20th century, physicists discovered that light is not only a wave. It also comes in tiny, indivisible packets, little grains of light called photons. A dim enough light source does not send a smooth wave. It sends photons one at a time, like a slow drip from a tap. And matter, it turned out, has the same double nature. An electron, which we picture as a tiny particle, a speck of solid stuff, can also behave like a wave. Electron diffraction was demonstrated by Davison and Germer in 1927. By 1961, Claus Johnson had sent electrons through a genuine double-slit setup. The particles of matter, the very things we imagine as the small, solid bricks the world is built from, produced the striped interference pattern that belongs to waves. This is already strange, but there is a way to make peace with it, and for a while people did. Maybe, you might think, the electrons are jostling each other. Maybe when you fire a whole crowd of them through the slits at once, they bump and interact and somehow organize themselves into bands. It is a reasonable guess. It is the kind of guess that protects the comfortable picture of solid things behaving in solid ways. So physicists tested it. They turned the source down as low as it would go until the machine was releasing one single electron at a time, with long pauses between them. One electron leaves. It crosses the apparatus completely alone, with no other electron anywhere near it to bump into. It passes the wall with the two slits. It lands on the screen, and it makes a single tiny dot, exactly where a particle should one point, one impact, one solid little arrival. Then another electron, much later. Another dot, somewhere else. Then another. At first, the dots look random, scattered across the screen, like the first few drops of rain on dry pavement. But the experimenters were patient. They let the dots accumulate. Hundreds, then thousands, then tens of thousands of single electrons, each one fired alone, each one landing as a single point. And as the dots built up, a pattern emerged out of them. Not two stripes, bands. The same interference pattern, the same alternating bright and dark, assembled one lonely dot at a time. Akira Tonomura and his team captured this beautifully in 1989, recording the slow build of the pattern dot by dot, and it remains one of the most quietly unsettling things you can watch in all of science. Picture yourself standing at that screen, in the dark, watching it happen. A single dot appears, then nothing for a while, then another dot somewhere you did not expect. For the first dozen arrivals, you would swear you are watching pure randomness, particles scattering like the first drops of rain on dry pavement, with no design behind them at all. But you keep watching, and the dots keep coming, one at a time, each one alone, each one a single particle that crossed the apparatus completely by itself. And slowly, the way an image rises out of a photograph developing in a tray, the bands begin to show themselves inside the scatter. Bright lines where the dots crowd together, pale gaps where almost none land. The pattern was never present in any single dot. It was hidden in the arithmetic of thousands of lonely arrivals, and it can only be there if every one of those lonely particles somehow sampled both paths before it decided where to strike. There is no way to draw this on paper that keeps your ordinary picture of the world intact. If you say the particle went through the left opening, you cannot account for the bands. If you say it went through the right, you cannot account for them either. The only description that survives is the one that refuses to give the particle a path at all, the one in which it crossed as a spread of possibility through both openings at once and became a single point only at the instant it arrived. This is the quiet trouble at the bottom of everything else we will say tonight. Nothing was crowded, nothing was rushed, nothing was struck or jostled. One thing went through, entirely alone, and behaved as though it were many. Sit with what this means, because it is the first real crack in the floor. Each electron travels alone. There is no crowd to interfere with. And yet the pattern that forms is an interference pattern, the kind that can only happen when something passes through both slits at once and overlaps with itself on the far side. A single electron, it seems, does not go through the left slit or the right slit. It goes through both. It leaves as one thing, behaves on the way like a spread-out wave passing through two openings, and then arrives, again, as one thing, a single dot. The arrival is a particle. The journey is a wave, and the wave passed through both doors. Now try to picture a pebble doing that. Picture throwing a single stone at a wall with two windows, and the stone somehow going through both windows and interfering with itself, so that over many throws, the stones pile up in striped bands instead of two heaps. It is not just unusual, it is impossible for a solid, already there object with a definite location. A thing that is genuinely in one place cannot pass through two separated openings at the same time. And yet the electron does exactly this, reliably, every time the experiment is run, in laboratories all over the world. For a while, you could still tell yourself this was a quirk of the very smallest things. Electrons are tiny and weird. Perhaps the rules are simply different down there, and it has nothing to do with the solid world we live in. But the experimenters kept pushing the size upward. They sent whole molecules through. In 1999, a team working with Anton Zeilinger sent carbon-60 molecules, soccer ball-shaped cages of 60 carbon atoms, around 720 units of atomic mass, each through an interference setup, and the molecules interfered, passing through both paths like waves. Then, in 2019, a group led by Markus Arndt in Vienna pushed it much further, sending molecules built from roughly 2,000 atoms, with masses beyond 25,000 atomic mass units, more than 40,000 protons, neutrons, and electrons bound together into one object. Even those behaved like waves. Even those went through both doors. These are not abstract specks. These are molecules large enough that, if the trend continued, you can begin to imagine objects you might almost see, and every one of them, when no detector is watching its path, refuses to commit to a single location. Each one behaves as though it has no definite position at all, until it lands. So here is where the first part of our question lands tonight. The world, at its smallest, does not act like a collection of solid things sitting in definite places. It acts like something spread out, undecided, holding several possibilities at once. The electron between the source and the screen is not secretly in one slit, hiding its location from us. As far as the experiment can tell, it is not in one place at all, which raises the obvious next question, the one that turns this from a curiosity into something that should make the floor feel less steady under you. If the electron goes through both slits when no one is watching its path, what happens if we simply watch? What happens if we put a tiny detector at each slit and catch the electron in the act of choosing a door? The answer is the strangest part so far, and it is where looking stops being innocent. Part 3. The moment looking changes the answer. So we try the obvious thing. We decide to catch the electron in the act. We set up the same double-slit experiment, firing electrons one at a time, building up the interference pattern that tells us each one went through both openings. But this time, we place a small detector at the slits, a device that can register which slit each electron actually passes through. We are not trying to block anything. We are not trying to interfere. We only want to know the path. We want to peek, to confirm with our own instruments what the electron is doing on its way through. Surely, you think, this is harmless. Surely knowing the path cannot change the path. The electron does what it does. We are only reading the label. The interference pattern disappears. The moment the detector is switched on and able to tell which slit each electron went through, the bands vanish from the screen. In their place, you get exactly what your old intuition wanted all along. Two stripes, one behind each slit, the pattern of solid particles, each going cleanly through one door. The electrons stop behaving like waves. They start behaving like pebbles. The wave nature does not just fade a little. It is gone, replaced by ordinary particle behavior, as if the electrons knew they were being watched and decided to play it safe. Then you turn the detector off again. The bands come back. The interference returns. Switch the watcher on, and the electron is a particle going through one slit. Switch the watcher off, and the electron is a wave going through both. You can do this again and again, and the world will keep answering the same way. The single variable that decides whether matter behaves like a spread-out wave or a localized particle is whether or not its path is being observed. This is the observer effect, and it is the first place where the gentle word looking starts to feel heavy. I want to be very careful here, because this is exactly the point where the idea gets twisted, and we are going to spend real time later untwisting it. When physicists say the electron behaves differently when it is observed, the temptation is to imagine that human attention itself, the conscious gaze of a person, is reaching out and changing the world. It is a thrilling thought. It is also not what the experiment shows, and we will come back to why. For now, hold this fact precisely as it is. What changes the outcome is not a pair of human eyes. It is the presence of a device that acquires information about which path the electron took. The detector can be a piece of equipment in a sealed box. No person ever has to look at its reading. As long as the which path information exists somewhere in the world, the interference is gone. That distinction matters enormously, and most popular descriptions get it wrong. The experiment is not telling us that consciousness alters matter. It is telling us something stranger and more precise. It is telling us that the act of a system becoming entangled with its surroundings in a way that records its path, the act of information about its position coming into existence, is what forces the electron to behave like it, has a definite path. When nothing in the universe knows which slit the electron went through, the electron goes through both. When something, anything, even a lifeless detector, registers the path, the electron goes through one. Let that reframing settle, because it changes the whole question. It is not really about eyes at all. It is about whether the world has, in some physical sense, taken note. And that is a far stranger and far more disturbing idea than a person staring at a particle. It suggests that the difference between a world of fuzzy possibilities and a world of definite facts is the difference between information not existing and information existing. You can sharpen the strangeness even further. Physicists have built versions of this experiment where the detector is extraordinarily gentle, where it barely touches the electron at all, only weakly hinting at the path. And what they find is a smooth trade. The more clearly the path is known, the more the interference fades. The more the path information is blurred, the more the interference returns. It is as though wave behavior and definite path behavior are two ends of a single seesaw, and the amount of information the world holds about the electron is the hand pressing on one side or the other. Knowledge and waviness cannot both be full at once. The world seems to enforce a budget. Think about how peculiar that budget is. In the ordinary world, knowing about a thing and the thing itself are completely separate. You can learn the exact temperature of a cup of water without changing the water by a single degree. Your knowledge sits over here, the water sits over there, and the two never trade places. But in the double-slit experiment, knowledge and reality are tied together by a fixed exchange rate. The more sharply the world knows which path the particle took, the less the particle behaves like a wave, and the trade is exact, dialed smoothly from one extreme to the other. It is as if reality has only so much definiteness to spend, and every bit of it spent on knowing the path is a bit subtracted from the spread of possibility. This is the first hint of something we will keep meeting tonight, the suspicion that information is not a description laid over the world, but somehow part of the fabric of the world itself. When you ask what happens when no one looks, you are really asking what the world is like when none of that budget has been spent, when no information about the particle exists anywhere, and the honest answer the experiment gives is that the particle, in that condition, is not anywhere in particular at all. Now, if you are looking for a comforting way out, there is one more left, and it is worth taking seriously because it is exactly the escape that the greatest physicists reached for. Maybe, you might say, the detector physically disturbs the electron. Maybe to detect a tiny particle, you have to bump it with something, a photon, a field, and that bump is what scrambles the delicate wave and destroys the pattern. In that picture, the world is still simple and already there. The electron always had a definite path. We just cannot measure it without clumsily knocking it around, like trying to feel for a soap bubble in the dark and popping it the moment you touch it. The observer effect would just be measurement clumsiness, nothing more than that. This is a beautiful, sensible objection, and for a few decades it let people sleep. If the strangeness is only that measuring disturbs, then realism survives. The world is still solid. We are just heavy-handed guests, but the experiments we are going to reach soon take that escape away. They show that the disturbance story, comforting as it is, cannot be the whole truth, because the loss of interference can be made to happen without any disturbance at all, and, more shockingly, it can be undone after the fact, after the electron has already landed. Before we get there, though, we need to confront just how far the strangeness reaches, because so far we have been talking about electrons and molecules, things small enough to dismiss. We have been able to keep the weirdness at arm's length, down in the microscopic basement of the world. A physicist named Erwin Schrodinger refused to let us keep it down there. He built a thought experiment designed to drag the strangeness up out of the basement and into the living room to a scale you cannot ignore. He did it with a box, a little bit of radioactive material, and a cat. And he did not build it to amaze you. He built it because he thought the whole idea was so absurd that putting a cat inside it would force everyone to admit the theory could not possibly mean what it seemed to mean. He may have been right that it is absurd. He was wrong that it would go away. Part 4. What we mean when we say, someone is watching. We have to slow down now and be very precise about a single word, because almost every confusion about this subject grows from it. The word is observation. When people first hear that a particle behaves differently when it is observed, they reach naturally for the most human meaning of the word. They picture a scientist leaning over the apparatus, eyes narrowed, and they imagine that the focused attention of a conscious mind is what reaches across the lab and changes the particle. It is an intoxicating idea. It seems to place human awareness at the very center of physical reality, to make us participants in the making of the world rather than spectators of it. And as we will see, a few serious thinkers genuinely entertain this. But if we let that meaning of the word in too early, we will misunderstand everything that follows. So let us pin the word down. In physics, to observe something does not mean for a person to become aware of it. To observe means to interact with it in a way that produces a record. It means that the state of the thing being looked at becomes tied to the state of something else, a detector, a stray photon, a molecule of air, the surrounding environment, such that, in principle, the path or the property could be read off from that something else. The technical word for this tying together is entanglement, and we will return to it, but the plain version is this. A measurement happens when information about a system spreads into the world. The instant the universe, anywhere, holds a usable record of which slit the electron went through, the electron behaves as though it took one slit. No human awareness is required at any step. This is why I keep insisting on a small but crucial phrase, and I want you to carry it with you for the rest of tonight. Looking is not the same as seeing. Seeing is what a conscious mind does. Looking, in the way the quantum world responds to it, is something a lump of metal can do, something a single particle of light can do, something the cold, dark room around you is doing constantly, without any mind present at all. The electron does not care whether you understand the reading on the detector. It only cares whether the reading exists. Once you accept that, the observer effect stops sounding like magic and starts sounding like something even harder to live with. Because now the question is not, why does my attention change the world? The question is, Why does the mere existence of information about a thing change what that thing is? Why should a particle have a definite path only once the universe has written that path down somewhere, and no definite path at all when the universe has not? To feel the full weight of this, we need a clear word for the in-between state, the condition of the electron when no path information exists. That word is superposition. A superposition is not the electron secretly being in one place while we remain ignorant of which. It is the electron genuinely holding several possibilities at once, in a way that has real, measurable consequences. We know it is not mere ignorance, because the possibilities interfere with each other, and you cannot interfere with a possibility that is not, in some sense, present. If the electron were really in one slit all along, and we simply did not know which, there would be no interference bands. The bands are the fingerprint of both possibilities being real at the same time. So, superposition is a real physical condition of holding open several answers, and measurement is the event that closes them down to one. The mathematics describes this with extraordinary precision, and it is worth knowing the shape of it even without the symbols. A quantum system is described by something called a wave function, written with the Greek letter psi. The wave function contains all the possibilities and how much each one counts. And it evolves smoothly, predictably, gracefully, following an equation discovered by Schrodinger. If you leave the system alone, the wave function just flows along, spreading and combining, every possibility evolving together in perfect order. There is nothing random or fuzzy about this part. It is as clean and deterministic as a planet moving along its orbit. The probabilities come in at the very last step, the step of measurement. When you measure, you do not get the smooth spread of the wave function. You get one definite outcome, and the chance of each possible outcome is given by a simple rule discovered by Max Born in 1926. The probability of an outcome equals the square of that part of the wave function, a quantity written as psi squared. So the theory has two completely different gears, between measurements, smooth and deterministic. At the moment of measurement, a sudden jump to one random outcome, with odds set by the Born rule. And here, exactly here, is the wound at the center of the most successful theory in the history of science. Nothing in the smooth equation ever produces the jump. The Schrodinger equation, left to run, never turns many possibilities into one outcome. It just keeps all of them flowing forever. The collapse to a single result, the thing that happens every time we look, the thing that gives us the definite world we live in, is bolted onto the theory by hand. It is an extra instruction that says, when a measurement occurs, pick one. But the theory never says what a measurement is. It never says when the jump happens, or what triggers it, or where the line is between the quantum world that holds possibilities open and the everyday world of single definite facts. This gap has a name. It is called the measurement problem, and it has gone unsolved for roughly a century. Think about how astonishing that is. We have a theory so accurate that in some predictions, it matches experiment to about 1 part in a trillion. It built the transistor and the laser. It explains the chemistry of every substance you have ever touched. It is, by any honest measure, the most precisely confirmed description of nature humans have ever produced. And sitting in the very middle of it is a hole so large that the people who use the theory every day cannot agree on what it means for something to be real when it is not being measured. They use the theory flawlessly and disagree completely about what it is telling them. This is the strange double life of quantum mechanics. As a tool, it is perfect. As a picture of reality, it is a riddle that has defeated every great mind that has approached it. You can calculate with it for a lifetime and never once need to decide whether the electron is really in 2 places. The arithmetic does not care. But the moment you ask the human question, is the thing actually there, in a definite state, when no one and nothing is measuring it, the theory falls silent, and into that silence rush a dozen rival answers, each defended by serious physicists None of them yet provable. We are going to meet those rival answers. But before we do, we have to understand why this matters so much that one of the founders of the theory tried to kill it with a thought experiment so vivid it has become the most famous image in all of physics. He took the strangeness of the small and tied it, with cruel elegance, to the life and death of an ordinary animal. He wanted to show that if you took the theory literally, it produced something monstrous. He wanted everyone to recoil. What he could not have known is that the monster would refuse to die. Part 5. The cat that is neither alive nor dead. Erwin Schrödinger was not a critic of quantum mechanics from the outside. He was one of its architects. The very equation we just described, the one that governs how the wave function flows, is his. So when he raised an objection, it carried the weight of a parent worried about something they had helped create. In 1935, Schrödinger described a scenario meant to expose what he saw as the absurdity of taking superposition seriously. Imagine a sealed steel box. Inside the box, you place a cat, alive and well. You also place a small amount of a radioactive substance, a tiny sample, chosen so that over the course of an hour, there is a 50-50 chance that a single atom in it will decay. Radioactive decay is a genuinely quantum event, governed by exactly the superposition rules we have been discussing. An atom that has not yet been observed is in a superposition of having decayed and not having decayed. Next to the radioactive sample, you place a detector. If the detector registers a decay, it triggers a hammer. The hammer shatters a small flask of poison. The poison kills the cat. Now close the box and wait 1 hour. Do not look inside. Here is Schrödinger's point. The atom, unobserved, is in a superposition of decayed and not decayed. But the atom is wired to the detector to the hammer to the poison to the cat. If we take the theory literally, the superposition should climb right up that chain. The atom is both decayed and not, so the detector both fired and did not, so the hammer both fell and did not, so the poison both released and did not. And so the cat, following the logic all the way up, is both dead and alive, not secretly one or the other, while we remain ignorant, but genuinely in a blended state of living and dead, in exactly the way the electron is genuinely in both slits. Only when you open the box and look does the superposition collapse, and the cat become, suddenly, definitely, one thing. Schrödinger thought this was ridiculous, and he meant it to sound ridiculous. A cat is not a subatomic particle. A cat is a warm, breathing, ordinary creature, and the idea that it could hang in a smear of alive and dead, waiting for a human to open a box before nature makes up its mind, struck him as a clear sign that something in our understanding had gone wrong. He was holding the strangeness up to the light and saying, "Look how foolish this becomes when you scale it up. Surely no one believes the cat is really both. Surely the cat settles the matter for itself, poison or no poison, long before anyone opens the lid. And your every instinct agrees with him. Of course the cat is already alive or already dead. Of course opening the box only tells you which. The cat is not waiting on your attention to decide whether it is breathing. This is realism roaring back, demanding its rights. The world is already in a definite state. Looking only reveals it. But here is the trap Schrödinger walked into, and it is the reason his cat became famous as a puzzle rather than as a punchline. He assumed everyone would agree the cat scenario is impossible, and that this agreement would force physicists to abandon the literal reading of superposition. Instead, the theory held. Every time someone tried to draw a clean line to say, superposition is real for atoms but somehow forbidden for cats, they could not find where the line was, or why it should exist, or what physical law enforced it. Nothing in the mathematics marks a boundary between the small things that are allowed to hold possibilities open and the large things that are not. The equation that puts the electron in both slits puts the atom in both states, and the atom is wired to the cat. If you believe the electron, the logic drags you, unwilling, all the way to the cat. People have spent decades looking for the place where the line should be drawn, and the search itself is part of what makes the cat so stubborn. Surely, the thinking goes, there must be some size, some level of complexity, some number of atoms, beyond which the rules change and superposition is simply no longer allowed. Below the line, the quantum world of held-open possibilities. Above it, the solid world of single definite facts, where cats are only ever alive or only ever dead. It is a comforting thought, and physicists have hunted for that boundary for the better part of a century. They have not found it. There is nothing in the mathematics that marks a cutoff. The same equation that governs the single electron governs the atom, and the molecule, and the detector, and the hammer, and the flask, and in principle the cat, with no natural stopping point written anywhere into it. Every time someone proposes a hard edge between the small and the large, someone else builds an experiment that pushes superposition to a still larger scale, and the proposed edge quietly retreats. We have already seen molecules of thousands of atoms behave like waves. The line, if it exists at all, keeps moving outward as our experiments improve, which is exactly what you would expect if there were no line to begin with, only a gradual hiding of the strangeness, as objects grow large enough to be touched by everything around them. And so the cat remains, not as a joke that physics outgrew, but as the sharpest way anyone has ever found to ask where the world of maybe becomes the world of is. So the cat did not kill the theory. The cat became a permanent question mark, a way of asking, out loud and in a form no one can forget, the exact thing we keep circling tonight. Where and how and why does the world of open possibilities become the world of single, definite facts? At what point does both become one? The honest answer, even now, almost 90 years later, is that nobody knows. We know the cat, when we open the box, is always definitely one thing. We do not know whether it became that one thing when we opened the box, or when the poison detector clicked, or whether, in some sense the theory permits, it remains both until something far larger settles it. There is one piece of modern understanding that takes the sharpest edge off the cat, and in fairness, we should name it now, even though we will develop it properly later. A real cat is not isolated. It is constantly interacting with its surroundings, with the air in the box, with the warmth of its own body radiating outward, with countless particles touching it every instant. And these interactions, as we will see, are themselves a kind of measurement. The world is touching the cat all the time, recording its state in a billion tiny ways, whether or not a human ever opens the lid. This process, called decoherence, makes the alive and dead mixture collapse for all practical purposes almost instantly. So no real cat ever hangs visibly between life and death for an hour. The strangeness is hidden far faster than that. But notice what decoherence does and does not do, because this will matter enormously by the end of tonight. It explains why we never see a blurred cat. It explains why the strangeness stays hidden. What it does not obviously do is explain why, out of the two possibilities, we end up experiencing exactly one. It tells us why the cat looks definite. It does not, by itself, tell us how nature chooses alive over dead, or whether the other possibility simply went somewhere else. The hole in the theory shrinks under decoherence, but it does not close. Schrodinger built his box to make people laugh at the theory and walk away. Instead, his cat sat down in the middle of physics and refused to leave, and it is still sitting there. And while it sat, a far more formidable opponent of the theory was sharpening a different and more profound objection. He did not bother with a cat. He went after the thing that mattered most to him, the thing he was not willing to give up under any circumstances. He went after the idea that the world is real whether or not we look. His name was Albert Einstein, and he was about to ask a question so simple that a child could understand it, and so sharp that it would take physicists 50 years to answer. Part 6. The argument Einstein refused to lose. Albert Einstein could not accept it. Not the mathematics, he respected the mathematics. What he could not accept was what the mathematics seemed to be saying about reality. Einstein had spent his life uncovering hidden order in the universe. He had shown that space and time bend, that mass and energy are the same thing wearing different clothes, that light comes in packets. He was no stranger to ideas that overturned common sense, but quantum mechanics, as it matured in the 1920s and 30s, asked him to give up something he held as nearly sacred. It asked him to accept that the properties of things are not definite until they are measured, that the world at its base is a matter of probabilities rather than facts, and that until you look, there may be no answer to the question of where a particle is or what it is doing. To this, Einstein famously objected that God does not play dice with the universe. The line is often quoted as if it were about gambling and randomness, and it was partly that. But underneath the dice was something he cared about even more. Einstein believed in a real world, out there, with definite properties, independent of observation. He believed the moon has a position, whether or not anyone is looking at it. He once asked a colleague, the physicist Abraham Pais, walking home one evening, whether he really believed the moon exists only when he looks at it. To Einstein, the answer was so obviously yes, of course it exists, that any theory suggesting otherwise had to be incomplete. Not wrong, necessarily. Incomplete, missing something. There must, he felt, be hidden details, underlying variables the theory had not yet captured, that fix the properties of things in advance, so that measurement only reveals what was already settled. Hold on to Einstein's question, because we are going to return to it at the very end of tonight, and its meaning will have changed by then. Is the moon there when nobody looks? Tonight, that question is going to travel a long way. In 1935, the same year Schrodinger described his cat, Einstein, and two younger colleagues, Boris Podolsky and Nathan Rosen, published a short, devastating paper. It is known by their initials as the EPR paper, and its purpose was to prove that quantum mechanics could not be the complete story. Their argument leaned on a phenomenon that Einstein found especially intolerable, a phenomenon that lies at the dark center of everything we are discussing. That phenomenon is entanglement. Here is what entanglement means, stripped to its bones. You can prepare two particles together in such a way that their properties are linked, even after you separate them and carry them far apart. Suppose two particles are created so that a certain property must be opposite for the two of them. If one is found to be up, the other must be down, and the reverse. Quantum mechanics says that before measurement, neither particle has a definite value of this property. Both are in superposition, both holding both possibilities open. But the instant you measure one and find, say, up, the other particle is immediately, definitely down, no matter how far away it is. You could carry one particle to the far side of a continent, or in principle the far side of the galaxy, and the moment you measure the near one, the distant one's property is settled. Einstein found this unbearable, and he had a sharp name for it. He called it spooky action at a distance. To him, it looked as if measuring one particle reached out instantly across any gap to fix the other, faster than light, which his own relativity forbade. And so he reasoned as follows. Since no influence can travel faster than light, the distant particle could not possibly be waiting on my measurement to decide its value. Therefore, its value must have been set all along, from the moment the pair was created. Both particles must carry hidden instructions, fixed in advance, telling them how to answer when measured. The correlation is no more mysterious than a pair of gloves. If I mail one glove to a friend across the world, and keep the other in a box, then the instant I open my box and see a left glove, I know my friend has the right one. Nothing spooky travelled. The gloves were always left and right. We just had not looked. Everything Einstein cared about is packed into that little story, and it is worth being clear about what he was defending because it was not a small thing. He was defending the idea that the world is the kind of place where explanations bottom out in real, local facts. A glove is left-handed because it was made left-handed. The fact lives in the glove, travels with the glove, and is simply uncovered when you look. Einstein wanted the universe to be like that all the way down, a place where every correlation, no matter how strange it seems, traces back to properties that things genuinely possess and carry with them through space. That is what he meant by a complete theory. Quantum mechanics, with its talk of values that do not exist until measured, looked to him like a temporary stand-in, a useful set of recipes that would eventually be replaced by a fuller description in which the gloves were, once again, just gloves. He was not being stubborn or old-fashioned. He was holding the line for the most reasonable picture of reality anyone has ever had. The tragedy and the wonder is that the line could finally be tested, and that the universe, when asked, came down on the other side. This is a powerful argument, and for 30 years it sat as a genuine open standoff. Einstein said the particles carry hidden instructions set in advance, which would mean the world is real and definite after all, and quantum mechanics is merely an incomplete description of a more fundamental, ordinary reality. The defenders of quantum mechanics, chiefly Niels Bohr, insisted there are no hidden instructions, that the particles genuinely have no definite values until measured. Both sides agreed on every experimental prediction. The disagreement seemed purely philosophical, a matter of taste about what was really going on behind the numbers, untestable, perhaps forever. You could choose the comforting Einstein picture or the strange Bohr picture, and no experiment could tell you which was right. That is where the matter rested, and it might have rested there permanently, a permanent draw between two views of reality, if not for a quiet, careful physicist from Northern Ireland who, almost 30 years later, did something everyone had assumed was impossible. He found a way to turn the philosophical question into a number you could measure. He found a way to ask the universe, directly, in an experiment, whether the particles carry hidden instructions set in advance, or whether they truly have no definite values until you look. He worked out exactly what the answer would be in each case, and the two answers were different enough to test, different enough to settle, once and for all, whether Einstein's comfortable moon was really there in the dark. His name was John Stuart Bell, and the door he opened did not lead where Einstein hoped. Part 7. The experiment that closed the last door. For almost 3 decades, the question of whether the particles carry their answers in advance was considered a matter of philosophy, the kind of thing you argued about over coffee and never resolved. John Stuart Bell changed that in 1964, and he did it with a piece of reasoning so clean that once you see it, you cannot unsee it. Bell took Einstein's own picture seriously. He said, "All right, suppose Einstein is correct. Suppose each pair of entangled particles is created, carrying hidden instructions, a complete set of predetermined answers for any measurement that might be made on them. This is what fairness to Einstein requires. Call this a theory of local hidden variables. Local, because nothing travels faster than light. Hidden, because the variables are details the quantum description has not captured. In this picture, the particles are like the pair of gloves, settled from the start, and the spooky correlation is no mystery at all." Then Bell asked a question nobody had quite thought to ask. He said, "Let us not just measure the particles in one fixed way. Let us measure them at different angles, and let us vary those angles independently for the two particles, and let us do this many, many times, and keep careful track of how often the two results agree." And he proved something remarkable. If the particles really do carry predetermined local instructions, then the pattern of agreements across all those different angles must stay within a certain limit. There is a ceiling on how strongly the results can be correlated. This ceiling is now written as a mathematical statement called Bell's inequality, and in one common form, the strength of correlation for any local hidden variable world cannot exceed the number 2. Then Bell calculated what quantum mechanics predicts for the very same measurements. And quantum mechanics breaks the ceiling. It predicts correlations stronger than any world of predetermined local answers could ever produce, reaching up to a value of about 2.8, the number 2 times the square root of 2, a limit later named the Tsirelson bound. The two pictures of reality no longer made the same predictions. Einstein's world of particles carrying answers in advance, and Bohr's world of particles with no definite values until measured now, gave different numbers for a real, doable experiment. The philosophy had become physics. You could go into a laboratory and ask nature directly. It took time to build experiments good enough to ask cleanly. The first serious attempts came from John Clauser, working in the early 1970s with Stuart Friedman in 1972. Their results already leaned against Einstein. Then, in 1981 and 1982, Alain Aspect in France performed a far more refined version, and crucially, he added a twist that sealed an important gap. He arranged to change the measurement angles while the particles were already in flight, too late for any signal traveling at the speed of light to warn one particle about how the other was going to be measured. This shut the door on the idea that the particles were somehow coordinating their answers through ordinary, slower-than-light communication. And still, the results matched quantum mechanics. The ceiling was broken. The inequality was violated. Now, for decades, there were two technical escape routes left, two loopholes a determined defender of the old picture could point to. One was the possibility that the particles were somehow influencing each other through some sublight channel after all. The other was that the detectors were only catching a fraction of the particles, and maybe the ones they missed would have restored the old limit. For years, experiments could close one loophole or the other, but not both at once, leaving a sliver of room for doubt. Then, in 2015, several teams closed both loopholes at the same time. A group in Delft, led by Ronald Henson, used entangled electrons in diamonds separated by more than a kilometre. Teams in Vienna, led by Marissa Justina, and at the United States National Institute of Standards and Technology, led by Lyndon Sharm, did it with photons. All of them, independently, with the last loopholes shut, found the same thing. Bell's inequality is violated. The world is not made of particles carrying predetermined local answers. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger, in the official words of the committee, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The highest honor in physics was given, in part, for proving that Einstein's comfortable picture of reality is wrong. I want you to feel the size of this, because it is one of the genuine turning points in the history of human understanding, and it usually gets buried under technical language. For most of history, every thinking person assumed the world is simply there, made of things with definite properties, whether or not anyone observes them. Einstein, perhaps the greatest physicist who ever lived, staked his position on exactly that assumption and tried to prove the strange new theory incomplete. And the universe, asked directly, in laboratory after laboratory, answered against him. There is no version of reality in which particles quietly carry all their properties in advance, locally, like gloves in boxes, waiting to be revealed. That world has been ruled out, not doubted, not questioned, ruled out by experiment to extraordinary precision, with every loophole sealed. This is the place where the floor we started on finally gives way, and I want to let it give way gently because it is a strange thing to absorb. We are not saying that we have failed to prove the world is real and definite when unobserved. We are saying something far stronger and far harder. We have proven that it is not real and definite in the way you always assumed. The choice the experiments leave us is stark. Either the properties of things are genuinely not settled until they are measured, or there are influences that act instantly across any distance, ignoring the speed of light, or both. Every one of the remaining options requires surrendering something that felt like bedrock. The one option that is no longer on the table is the one almost everyone believed their entire lives, the one Einstein fought for, the cozy, obvious world that is simply already there. It is worth pausing on the gloves, because the gloves were Einstein's best hope, and the gloves are exactly what Bell took away. Remember the picture. A pair of gloves, one mailed across the world, one kept in a box. The instant you open your box and see a left glove, you know your friend received the right one, and nothing spooky travelled, because the gloves were always left and right from the moment they were packed. This is how a sensible world is supposed to work. The correlation between distant things is explained by properties they carried with them all along. What Bell proved, and what the experiments confirmed, is that the particles are not gloves. If they were gloves, if they carried their answers packed inside them from the start, the strength of their agreement across many different measurement angles could never climb past a certain ceiling. The real particles climb past it, every time, in laboratory after laboratory. There is no set of properties you could pack into them in advance, no hidden instructions written at the moment of their creation that could reproduce what they actually do. The gloves are not gloves, and once you absorb that, you cannot get the simple world back. You are left standing in a reality where things genuinely do not carry their properties around with them, settled and waiting, the way you have assumed about every object you have ever touched. Let that sit, slowly, without panic. The world did not end when this was discovered. The sun still rose. But the picture of the world that everyone carried in their chest, the picture of a place that is fully and definitely there, whether or not anyone looks, had quietly been proven false, and almost no one outside of physics ever noticed. Sit with that for a moment, in the quiet. The world you have always pictured, continuing on, without you, fully formed, complete, definite, indifferent to whether anyone looks, that exact world has been closed off by experiment. Whatever reality is, it is not that. And if it is not that, then the question we have been carrying since the first minute is no longer a child's question or a philosopher's game. What happens when no one looks has become a question with no comfortable answer left. But the experiments were not finished surprising us, because the next thing physicists discovered was that it is not only the present that refuses to be definite. Under the right conditions, even the past seems to remain open, waiting, until a choice is made, and the choice can be made after the particle has already finished its journey. Part 8. The choice that reaches into the past. We left ourselves one comforting idea a while ago, and now we have to take it back. The idea was that the observer effect might just be clumsiness, that detecting a particle must physically jostle it, and that the jostling is what destroys the wave behavior. If that were true, the world could still be ordinary underneath, just delicate and hard to measure without disturbing. The experiments in this part remove that comfort, and they do it in a way so strange that when you first meet it, it sounds like a trick. Start with something called the quantum eraser. The setup uses entangled pairs of photons. One photon of each pair, the one we will call the signal, is sent toward a double slit-style apparatus. The other photon of the pair, the one we will call the idler, is sent off in a different direction toward a separate set of detectors. Now here is the key. Because the two photons are entangled, the idler carries information about which path the signal photon took. So even though no one watches the signal photon directly, the which path information exists, encoded in its distant partner. And as we now expect, when that information exists, the signal photons show no interference. They behave like particles. The path is, in effect, known, so the wave behavior is gone. Then comes the move that breaks the clumsiness, explanation. The experimenters arrange the idler photons so that, by choosing a particular way of detecting them, they can erase the which path information, scramble it so thoroughly that it becomes impossible, even in principle, to tell which path the signal took. And when they do that, the interference pattern comes back among the matching signal photons. Erase the knowledge, and the wave behavior returns. The signal photons themselves were never touched by this choice. Nothing was done to them. Only the information held by their distant partners was either kept or erased. And whether the wave behavior appears depends entirely on whether that information survives anywhere in the world. That alone should bother you, because it shows the loss of interference was never about physical disturbance. The signal photons were not jostled into behaving like particles. They behaved like particles whenever the path information existed, and like waves whenever it did not, regardless of any bump. The thing that matters is not whether you touched the particle. The thing that matters is whether the universe holds a record of which way it went. Now comes the part that loosens time itself. This experiment was first carried out by Yoon-Ho Kim and colleagues, working with Marlon Scully, and published in the year 2000. In their version, the choice to keep or erase the which path information was made after the signal photon had already been detected. The signal photon's journey was over. It had already landed. It had already, in the everyday sense, finished being whatever it was going to be. And only then was the idler photon detected, and only at that later moment was the which path information either preserved or erased. Yet whether the signal photons formed an interference pattern still depended on that later choice. The decision made after the signal had landed determined whether the signal had behaved as a wave or a particle. I have to be careful and honest here, because this is the exact spot where breathless accounts go off the rails. No information travels backward in time. No message is sent to the past. You cannot use this to change anything that has already happened in a way you could notice at the time, and there is no paradox, no grandfather you could prevent. If you only look at the signal photons by themselves, with no knowledge of their partners, you see a meaningless smear, no pattern at all. The interference pattern only appears when you sort the signal photons according to what was later done to their partners. So nothing spooky is sent backward that you could ever catch in the act. And yet the simple, comforting story that each photon had a definite nature, wave, or particle, fixed during its journey, settled, long before anyone made any later choice, that story cannot survive this experiment. The photon did not carry a fixed answer through its trip. The answer to what was it doing remained genuinely open until the which path information was finally either kept or erased, even though that happened after the photon was gone. The past, in the only sense the experiment can speak about, was not fully written until the choice was made. There is an even purer version of this idea, proposed by the physicist John Archibald Wheeler in 1978 and again in 1983. Wheeler imagined an experiment in which you decide whether to measure a particle as a wave or as a particle only after it has already entered the apparatus and committed to its path. He called it a delayed choice experiment. For years, it was only a thought experiment, but the technology caught up. It has now been carried out for real, first with photons by a team led by Vincent Jacques in 2007, and then, strikingly, with a single atom. In 2015, a group at the Australian National University, with Andrew Truscott and Andrew Manning among them, performed Wheeler's delayed choice experiment using one single helium atom, cooled to almost absolute zero, sent through an interferometer. They chose whether to look for wave behavior or particle behavior only after the atom was already inside, and every time the atom's behavior matched the choice made after it had entered. The experimenters' conclusion was blunt. It does not make sense, they said, to assign the atom a definite wave or particle nature before the measurement is made. The nature was not there in advance. It was settled by the late choice. Let me set you down inside this for a moment, because it deserves to be felt and not just stated. Picture the atom already on its way, already committed, its journey in any ordinary sense complete. There is nothing left for it to decide, you would think. And then, only then, the experimenter chooses which question to ask of it, and the atom's entire history arranges itself to answer that question, as though the past had been holding its breath, waiting to find out which version of events it would need to have been. No message races backward, no law of cause and effect is broken in any way you could exploit. And still, the thing you believed most firmly, that what happened already happened, fixed and finished, and beyond reach, quietly dissolves. The past, at this scale, is not a settled fact sitting behind you. It is a set of possibilities that stays open until the world forces it to choose. I want to guard you against the wrong lesson here, because it is an easy one to grab, and it is genuinely mistaken. None of this means you can change the past, or send a message backward, or undo something that has already happened to you. The universe is very careful to forbid exactly that. If you sit and stare only at the signal photons, with no knowledge of what was done to their distant partners, you see nothing but a featureless blur, no pattern, no signal, no hint of anything strange at all. The interference only appears later, when someone sorts those already recorded photons according to what was done to their partners afterward. So nothing usable ever travels backward in time. You can never catch the past in the act of rewriting itself. What dissolves is subtler and, in a way, harder to live with than time travel would be. It is the simple belief that the particle had a single, definite history, one true story of what it did, written and sealed the moment it happened. That belief, and only that belief, is what the experiment quietly removes. The events were real, the record is real, but the question of what the particle was doing on the way had no single answer until the world at last was forced to supply one. So now we have lost both comforts. We lost the idea that the world is definite when unobserved, back when Bell's experiments closed that door. And now we have lost the idea that at least the past, once it happens, is fixed. Even the past, it seems, can wait on a measurement. At this point, a very natural and very human thought arrives, and it has occurred to nearly everyone who has ever sat with these experiments, including some of the founders of the theory itself. If reality seems to wait until a measurement is made, and if measurement is the moment that fuzzy possibility becomes definite fact, then maybe the thing that completes the measurement, the thing that finally turns maybe into, is the one thing in this whole story we have been carefully keeping out of it. Maybe it is us. Maybe it is the mind. Maybe consciousness is what the universe has been waiting for. It is a beautiful idea. It is the idea hiding inside our title. And we owe it a serious, honest hearing before we find out whether it survives. Part 9. The tempting idea that it is us. The idea that consciousness completes reality is not a fringe notion dreamed up by mystics with no physics behind them. It was taken seriously by some of the most rigorous minds in the history of the subject, and to understand why, we have to follow a chain of reasoning that is genuinely difficult to escape. It begins with a man named John von Neumann, one of the great mathematicians of the 20th century, who in 1932 laid out the mathematical structure of quantum mechanics with unmatched precision. Von Neumann looked carefully at the measurement problem and noticed something uncomfortable. When you measure a quantum system, you use a device. But the device is itself made of atoms, and atoms obey quantum mechanics. So the device itself should be describable by a wave function. When the device interacts with the system, it does not collapse anything. Instead, it becomes entangled with the system, and now the combined system plus device is in a superposition. The device's pointer is in a superposition of pointing at this result and that result. To read the device, you use a second device, or your eye, or a camera, but that too is made of atoms, and it too just becomes entangled, joining the superposition rather than ending it. This is the core of what is called the von Neumann chain. Every physical thing you bring in to make the measurement definite is itself a quantum system that simply joins the growing superposition instead of collapsing it. The detector entangles with the particle. The camera entangles with the detector. The computer entangles with the camera. The light from the screen entangles with your eye. Your retina entangles with the light. Your nerves entangle with your retina. At no point does the smooth, possibility-preserving equation ever produce a single definite outcome. The chain just grows longer and longer, sweeping more and more of the world into one enormous superposition. So where does it stop? Where does the actual collapse, the genuine becoming definite, finally occur? Von Neumann noticed that the mathematics lets you place the dividing line, the cut between the quantum part that stays in superposition, and the classical part where one outcome is real almost anywhere along the chain, and it makes no difference to your predictions. You can put it at the detector, or at the camera, or at the eye, and the numbers come out the same. The theory does not tell you where the cut belongs, but the chain has to end somewhere, because in your actual experience, you only ever see one result. You never see a superposition. Your conscious experience is always of a single definite outcome, and so a few thinkers drew the boldest possible conclusion. If the chain of merely physical things never produces a definite outcome on its own, and if the one place the chain undeniably terminates is your conscious awareness, then perhaps consciousness is where the collapse happens. Perhaps the entry of the result into a conscious mind is the event that turns possibility into fact. This idea was developed by Fritz London and Edmund Bauer in 1939, and most famously argued by Eugene Wigner, a Nobel-winning physicist, around 1961. In this view, the reason the world becomes definite is that minds observe it. Unobserved by any consciousness, the universe would remain an unresolved fog of possibilities. The act of a conscious being becoming aware is what crystallizes reality. The universe, in the strongest reading, needs a mind to look at it in order to be. You can see why this idea is so seductive and why it sits behind the question in our title. It places consciousness at the very foundation of physical reality. It suggests that mind is not a late, accidental arrival in a dead universe, but an essential ingredient without which nothing would be definite at all. It flatters something profound in us, the sense that our awareness matters, that the act of paying attention is somehow sacred. It turns the observer effect from a piece of laboratory bookkeeping into a statement about the cosmic importance of the watching mind. And for a brief period, it was a respectable position held by serious people. You can feel how hard it is to escape the chain, and that difficulty is the whole reason the idea ever earned its respect. Follow it once more, slowly, and watch how it traps you. The particle is in superposition. The detector that reads the particle is made of atoms, so when it interacts, it does not collapse the particle, it joins it, and now detector and particle together are in superposition. The screen that displays the detector's reading is also made of atoms, so it joins too. The light travelling from the screen to your eye is quantum, so it joins. The cells of your retina are quantum, so they join. The signals running up your optic nerve are quantum, so they join. At every single step, the honest application of the theory says the superposition does not end. It grows, swallowing each new piece of apparatus and each new stretch of the world into one enormous undecided state. And yet your actual experience, the thing you cannot deny, is always of one definite result. You never open your eyes to a blurred world. You never see both outcomes at once. So somewhere, the chain that the theory says should never break must break. And the only link in it that is undeniably different from all the others, the only place where merely physical stuff gives way to felt experience, is your own awareness. That is the reasoning, and you can see that it is not foolish. It is what you get when you take the theory at its word, and then notice that your inner life refuses to come in two copies. The mistake was not in noticing the chain. The mistake was in concluding that awareness must be the thing that ends it. So let us give it every chance, and then let us be honest about why it fell. The first problem is the one we have been quietly building toward since the third part of tonight. The observer effect does not actually require a conscious observer. The interference pattern disappears whenever the witch path information exists anywhere in the physical world, recorded by any device, whether or not a single mind ever becomes aware of the reading. You can seal the detector in a box, never look at its record, and the interference is still gone. A lump of equipment, a stray particle of light, a cold and mindless machine, all destroy the wave behavior just as effectively as a watching scientist. If consciousness were truly required to collapse the wave function, then a measurement no human ever observed should leave the superposition intact. It does not. The world becomes definite through interaction, not through awareness. This is the single most important sentence in tonight's entire story, and it is why I asked you, long ago, to remember that looking is not the same as seeing. The second problem is that the consciousness view leads to deeply awkward questions it cannot answer. If a mind is required to collapse reality, then which minds count? Does a human qualify, but not a cat? Does the cat in Schrodinger's box collapse its own fate, being conscious, or does it hang in limbo until a person opens the lid? What about an insect, a bacterium, a thermostat, a video camera? Where on the long ladder of complexity does mere physical entanglement suddenly become genuine awareness with the power to make reality definite? And worst of all, for billions of years before any conscious creature existed, the universe was forming galaxies, stars, and planets, processes we can reconstruct in detail from the physical record. If nothing definite can happen without a conscious observer, how did a lifeless cosmos manage to build the very brains that would later be needed to make it real? The picture seems to require minds to bring about the conditions for minds, a loop with no place to stand. Wigner himself, to his great credit, eventually abandoned the idea. He came to feel that letting consciousness collapse the wave function created more problems than it solved, particularly once the modern understanding of how the environment interacts with quantum systems began to take shape. The man most associated with the consciousness causes collapse view let it go. Today it survives mainly at the edges, and in a much louder and looser form out in the wider culture, where it has been stretched into claims that thought shapes physical reality, that you manifest your circumstances by believing, that the universe rearranges itself around your attention. A popular film in the early 2000s wrapped these claims in the language of quantum physics and sold them to millions. But the careful physics does not support any of it. The experiments say the world becomes definite when it is touched, recorded, entangled with its surroundings, not when it is loved or wished at or witnessed by a mind. So we have to set the beautiful idea down, not because it is stupid, but because the evidence does not bear its weight. The universe does not appear to be waiting for your eyes or anyone's eyes. And that leaves us with a harder, stranger, and in some ways lonelier possibility. Perhaps the world becomes definite all the time, everywhere, completely without us, because something else has been doing the looking all along. Something that never sleeps, never blinks, and is present in every corner of space. Not a mind. The rest of the universe itself. Part 10. The universe was never waiting for your eyes. If consciousness is not what makes the world definite, then we are left with a puzzle that seems even harder. Something turns possibility into fact. Something ends the superposition. If it is not the mind, what is it? The answer that most physicists now lean on is, in a way, the most humbling one of all. The thing that has been collapsing reality everywhere, in every instant, since long before there were eyes to see, is the rest of the universe itself. To understand this, we have to return to that growing chain of entanglement we met earlier, the one where the detector entangles with the particle, and the camera with the detector, and so on without end. We treated that chain as a problem, but look at it again, and notice something we glossed over. The chain does not wait politely for a scientist to start a measurement. It is happening all the time, to everything, whether or not any experiment is underway. Every object in the universe is constantly being touched by its surroundings. Light is bouncing off it. Air molecules are colliding with it. Heat is radiating from it. Even in the emptiest, darkest place you can imagine, the faint, leftover glow from the birth of the universe is passing through, brushing against every particle. Nothing is ever truly isolated. Everything is being touched constantly by the world around it. And every one of those touches is, in the precise sense we defined, a measurement. Each collision, each bounced photon, carries away a little information about where the object is and what it is doing. The object becomes entangled with its environment, and the environment is enormous, with countless particles flying off in all directions, each now carrying a tiny record. This process has a name. It is called decoherence, and it was developed by Heinz-Dieter Zeh beginning in 1970, and then worked out in beautiful detail by Wojciech Zurek across the 1980s and beyond. Decoherence is the reason the strangeness of the small world never seems to reach the large one. The superposition does not vanish. It leaks. It spreads out into the environment so quickly and so thoroughly that, for any object bigger than a molecule, the possibilities can no longer interfere with each other in any way you could ever detect. The speed of this is almost impossible to overstate. A small grain of dust floating in a room, struck constantly by air molecules and light, loses its quantum coherence in something like 1/10 million trillionth of a second. The numbers are so extreme that, for anything you can see with your eyes, the wave behavior is hidden faster than any clock could ever catch. This is why you never see a cup of coffee in two places, never watch a chair smear into a superposition, never catch the moon hovering in a fog of possible positions. The moon is being measured, ceaselessly, by sunlight and starlight and the ancient background glow of the cosmos, every single moment. The universe is watching the moon so thoroughly and so constantly that it never gets the chance to be indefinite at a scale you could notice. Let me put you inside this picture, because it changes how the dark feels. Imagine you could see every photon and every drifting molecule in a sealed, lightless room. You would not find stillness, you would find a storm. Light from the warm walls, infrared pouring off your own body, particles streaming and colliding without pause, and threaded through all of it, the faint relic radiation left over from the beginning of everything, still arriving from every direction. All of it is touching every surface, reading the state of every object, carrying that information away into the wider world. In this picture, there is no such thing as unobserved. There is no quiet corner where things go undecided. The universe has been watching itself, everywhere, all along, with no mind involved anywhere in the process. You were never the observer the world was waiting for. You were never required at all. Stay in that dark room a moment longer, because there is a strange comfort waiting on the far side of the strangeness. We tend to imagine that when we leave a room and close the door, the things inside fall into some kind of suspended uncertainty, holding their breath until we return to make them real again. That picture is simply wrong, and it was always wrong. The room you just left is not waiting for you. It is flooded, this very instant, with light bouncing off every surface, with warmth pouring from the walls, with countless particles arriving from the world outside and from the ancient glow that fills all of space. Every object in that room is being read continuously by an environment far more attentive and far more constant than any human watcher could ever be. The book on the table is being measured by the light that falls on it, whether or not your eyes are there to catch the reflection. The room does not dissolve when you leave. It is held in place by an audience of trillions, none of them alive, none of them aware, all of them watching in the only sense that matters to the physics. And so the loneliness of being unnecessary turns, if you let it, into something almost gentle. You were never carrying the world on the strength of your attention. You never had to. The universe has been keeping itself definite in every corner, through every long age before you were born, and through every hour you spend asleep, and it asks nothing of you in return. You are free to close your eyes. The world does not need you to hold it together. There is a refinement of this idea that is worth knowing, because it explains something the bare story leaves out. You might ask, if the environment is constantly measuring everything, why do different observers always agree about what they see? Why does everyone in the room agree the cup is on the left, if the underlying reality is a storm of entanglement? Zurek's answer is elegant. The environment does not just record an object's state once. It makes enormous numbers of copies, broadcasting the same information in every direction, in every photon that scatters off the object and flies away. So when you look, you are not disturbing the object. You are intercepting a tiny fraction of the countless copies of its state that the environment has already spread across the room. That is why we all agree. We are all reading from the same flood of copies. Zurek calls this quantum Darwinism, because the states that get copied most successfully into the environment are the ones that survive to become the everyday classical reality we share. The states that survive observation are, in a sense, the fittest. Now, I have to be careful and honest, because decoherence is sometimes oversold, and the honesty is part of why this subject is so haunting. Decoherence explains, beautifully, why we never see superpositions, why the large world looks definite and classical, why everyone agrees. It explains the appearance of collapse. What it does not quite do, on its own, is explain why, out of all the possibilities, you end up experiencing exactly one. It tells you the cup is no longer in a detectable superposition of left and right. It does not, by itself, tell you why you see left rather than right. The possibilities have stopped interfering, but the question of why a single one becomes your reality is still, at the most basic level, open. The hole in the theory has been made small. It has not been filled. And this is where the rival pictures part ways for good, each one accepting decoherence but disagreeing about what happens at that final step. One camp says that something genuinely random occurs, that nature truly rolls dice and picks one outcome, and that the others simply never happen. This is the view closest to how most people use the theory day to day, and it brings us right back to the thing that so troubled Einstein, the irreducible randomness at the base of reality, the dice he refused to believe in. If you have spent time with this channel before, you may remember we once followed that same randomness into the world of radioactive decay, where a single atom chooses its moment to break apart with no cause and no schedule, perfectly unpredictable on its own, yet perfectly regular across billions. The dice are real, this camp says, and the universe rolls them constantly, and the outcomes you did not get are simply gone. The other camp makes a stranger and bolder move. It says there is no collapse at all and no dice. It says the smooth equation is the whole truth, and it never stops being true. When a measurement happens, every possible outcome occurs. The wave function does not pick one. It splits, and you split with it. In one branch, you see the result come out one way, and in another branch, a version of you sees it come out the other, and both are equally real, and neither can ever reach the other. This is the many worlds idea, first proposed by Hugh Everett III in 1957. We have talked on this channel before about the possibility that ours is only one of countless universes. The many worlds picture is one route to that conclusion, born not from telescopes, but from taking the quantum equation absolutely literally and refusing to add anything by hand. In this view, the universe never becomes definite, because it never needed to. It simply contains every outcome at once, and your sense of a single definite world is just the view from one branch. There are gentler versions too. Some physicists, like Carlo Rovelli, argue that the properties of things are never absolute but only ever relative to whatever they interact with, so that asking what state something is in, with no reference to anything else, is a question with no answer. Others, in a view known as cubism, hold that the wave function was never a picture of the world at all, but a tool describing the expectations of whoever is using it, so that collapse is just a person updating their beliefs when a new experience arrives. Each of these is a serious attempt by serious people, and we will lay them side by side in a moment. But notice what they all share. Not one of them needs you. Not one of them needs a human mind, or any mind, to make the world definite. The environment does the measuring. The cosmos watches itself. Whether reality picks one outcome by rolling dice, or splits into all of them, or only ever exists in relation to other things, the special role we were tempted to give consciousness has quietly evaporated. The universe was running this process flawlessly for nearly 14 billion years before the first eye opened. It does not need ours now. And just when it seems we have at least found solid ground again, the comforting thought that even without us, the world becomes definite on its own. Through the patient watching of the cosmos, the experiments take one more step. They raise a possibility stranger than anything yet. They suggest that even the definite outcomes, the facts that the world settles on, might not be the same for everyone. That what actually happened might depend on who is asking. Part 11. Whose version of what happened is real. We have been assuming, through all of this, that whatever the answer turns out to be, at least a fact is a fact. Once the world settles on an outcome, once the cup is definitely on the left, that is simply true for everyone, everywhere. You and I might be uncertain about it beforehand, but after the measurement there is a single shared reality we can both point to. This is the last assumption standing, and the most unsettling experiments of recent years suggest that even this may not survive. The idea goes back to Eugene Wigner, the same physicist who once thought consciousness might collapse the wave function. In 1961, he described a scenario now known as Wigner's friend. Picture a laboratory, sealed off completely from the outside, and inside it a scientist, Wigner's friend, performing a quantum measurement, say, on a particle that can come out one of two ways. The friend makes the measurement and gets a definite result. For the friend, inside the lab, the matter is settled. The particle came out one way, the result is recorded. A fact now exists. But now consider Wigner, standing outside the sealed lab, who has not yet opened it or received any information from within. From Wigner's point of view, the lab and everything in it, the particle, the apparatus, and the friend, form one big isolated quantum system that nothing outside has interacted with. And the rules of quantum mechanics, applied honestly, say that an isolated system that has not been measured from outside is in a superposition. So from Wigner's perspective, the friend is in a superposition of having seen one result and having seen the other. The friend, inside, is certain a definite fact exists. Wigner, outside, must describe that same friend as an unresolved mixture of both outcomes. Two observers, one event, two genuinely different accounts of whether a fact even exists yet. For decades, this was a thought experiment, a paradox to argue about, and most people assumed it would dissolve once you thought carefully enough. Then, beginning around 2018, a series of physicists found ways to sharpen it into something far more dangerous, and even to test pieces of it. Daniela Frauchiger and Renato Renner published an argument in 2018 showing that if several observers in nested Wigner's friend situations each reason about each other using standard quantum mechanics, they can be driven to conclusions that flatly contradict one another. The theory, applied to observers who contain other observers, can produce statements that cannot all be true at once. It was a formal demonstration that something has to give, that you cannot have all of the comforting assumptions together. Then came the experiments. In 2019, a team led by Massimiliano Proietti carried out a version using 6 entangled photons, arranged so that some of the photons played the role of friends, making measurements inside sealed labs, and others played the role of outside observers. It was not a conscious human inside a room, of course, but a physical system standing in for the friend, performing and recording a measurement. And the results were consistent with quantum mechanics, which is to say they were consistent with the friends and the outside observers holding genuinely different accounts of what had happened. The experiment supported the conclusion, in the careful language of the paper, that the measurement outcomes cannot be treated as observer-independent facts. A year later, in 2020, a group led by Kok-Wei Bong, working with Howard Wiseman and others, pushed this further with what they called a local friendliness theorem. They laid out a set of assumptions even weaker and more reasonable than the ones Bell had used, assumptions you would think any sensible person would accept. One was simply that the result a friend records inside the lab is a real single fact. Another was that distant choices cannot instantly affect local results. And they proved that quantum mechanics, in a Wigner's friend setup, violates these assumptions too, and they confirmed the violation experimentally. The conclusion is genuinely staggering. To keep quantum mechanics, you may have to give up the idea that the outcome a sealed-off observer records is an absolute fact shared by everyone. What happened inside the lab might simply not have a single observer-independent answer. I want to slow all the way down and put you inside both points of view at once, because the discomfort is the whole lesson. Imagine you are the friend, sealed in the lab. You make the measurement. You see the needle settle. You write the result in your notebook. For you, this is as solid a fact as anything in your life. It happened. You saw it. Now drift outside the lab and become the colleague who has not yet opened the door. From out here, by the honest rules of the theory, the entire room, you and your notebook and your certainty included, remains an unsettled superposition, a state in which the measurement has not resolved into one answer at all. Hold both of these at the same time. Inside, a definite fact. Outside, no fact yet. Not two opinions about one underlying truth, but two descriptions that the theory says are each correct from where they stand. Do not try to resolve it. The fact that it will not resolve is exactly the point. This is a lonelier strangeness than anything we have met tonight, and it is worth naming what it costs. Uncertainty we can live with. Not knowing the answer is ordinary. The answer is still out there, waiting. But this is something else. This is the suggestion that there may be no single answer to wait for, that what really happened could be one thing for you and another thing for me, and that there is no higher vantage point from which one of us is simply right. Objectivity itself, the bedrock notion that there is one shared world of facts we are all living inside, develops a crack. The thing we lose here is not certainty. It is the guarantee that we are all even talking about the same settled past. Notice how quietly this dismantles something we never thought to question. All our lives we argue about the world on the assumption that there is one world to argue about. We may disagree about what happened, but we take for granted that something definite happened, a single sequence of events sitting in the past, and that our disagreement is only about who has read it correctly. The whole idea of evidence, of getting to the bottom of a matter, of finding out what really took place, rests on the belief that there is a what really took place, one shared and settled story underneath all our partial views of it. The Wigner's friend results put a small, cold question mark against even that. They raise the possibility that for some events, at the level where the theory is honest, there may be no single underlying story, only the friend's account and the outsider's account, each complete and correct from where it stands, with no fact of the matter joining them. This does not reach up into your daily life. You and I will always agree about the ordinary world because the environment floods it with so many copies of every fact that our views are locked together. But at the foundation, in the careful experiments, the seam shows. And once you have seen the seam, the solid floor of a single shared reality never feels quite as solid again. Now, I have to be honest about how far this goes, because this is the frontier, and the frontier is where humility matters most. These results do not prove that reality is a free-for-all, or that you can choose your own facts, or that nothing is real. They are careful, technical statements about what combinations of reasonable assumptions can survive together. And physicists are still arguing, right now, about exactly which assumption should be the one we surrender. Some say we give up the absolute objectivity of outcomes. Some say we accept that the world is genuinely non-local. Some say observers who are themselves in superposition simply cannot be reasoned about the way we reason about ordinary measurements. The debate is live, and no one has the final word. But every path forward requires letting go of something that, a century ago, every scientist would have called too obvious to question. So let us gather what we are carrying, now that we are near the end. We began with a world that was simply there, definite, complete, waiting whether or not anyone looked. We watched a single particle pass through two doors at once. We watched the act of recording its path turn it from a wave into a thing. We watched Schrodinger's cat refuse to be only alive or only dead. We watched Einstein insist the moon is there in the dark, and we watched the experiments answer him and close that door. We watched the past itself stay open until a late choice settled it. We were tempted by the idea that our own minds complete reality, and we found the evidence would not carry it. We discovered the universe has been measuring itself all along, with no need for us. And now we find that even the facts the world settles on may not be the same for every observer. Which brings us, at last, back to the question we have carried from the very first minute. What happens when no one looks? It is time to give the most honest answer that physics can give. And the honest answer is not the one you expected when we began. Part 12. The answer we do not have and the one in your hand. Here is the honest answer. Physics cannot tell you whether the universe exists when you are not looking at it. After a century of the most precise experiments human beings have ever performed, after closing every loophole and testing every assumption, the most basic question we started with remains open. We know, with certainty, that the comfortable old picture is wrong. We do not know what to put in its place. I want to lay out the choices plainly, side by side, because seeing them together is the closest thing to clarity this subject allows. Think of each one as a different answer to our single question. Does the world have a definite reality when no one and nothing is measuring it? The oldest answer, the one Niels Bohr championed, is simply to refuse the question. In this view, sometimes called the Copenhagen interpretation, it is meaningless to talk about the properties of a system before it is measured. There is no fact about where the electron is until you look. Asking what it was doing in between is like asking what is north of the North Pole. The question has no answer, because the world is not built to have one. This view is honest about the strangeness and declines to explain it, which many find unsatisfying and many others find admirably disciplined. The second answer is the one we already set down. The universe needs a conscious mind to become definite. We gave it a fair hearing, and the evidence did not carry it. The world becomes definite through interaction, not awareness, and so this answer survives mainly in the looser language of the wider culture rather than in the laboratory. The third answer is the one most working physicists quietly rely on. The universe needs interaction, not a mind. Reality becomes definite whenever a system entangles with its environment, whenever the world takes note in the physical sense, which is happening everywhere, always. In this view, there is nothing special about you, but there is also no fog of undecided reality waiting in the dark, because the cosmos is measuring itself in every instant. The moon is definite because sunlight and starlight and the ancient background glow are touching it without pause. It does not need your eyes. It has the whole universe for an audience. The fourth answer says the world always exists, completely, in every possibility at once, and never collapses at all. This is the many worlds view. Nothing is ever waiting, because nothing is ever undecided. Every outcome simply happens, each in its own branch, and your single definite experience is just the slice you happen to be riding. Reality is not too empty to be definite, it is too full. The fifth answer, the pilot wave picture worked out by Louis de Broglie and David Bohm, says that particles always have perfectly definite positions at every moment, observed or not, exactly as Einstein wanted. The moon is absolutely there in the dark, and so is everything else. But this answer pays a steep price for its comfort. To make the numbers work, it requires that everything be connected to everything else instantly across any distance, a thoroughgoing non-locality woven into the foundation of the world. You can keep your definite reality, but only if you accept that the universe is laced together by invisible threads that ignore space entirely. The sixth family of answers says the properties of things are real but never absolute, existing only in relation to whatever they interact with, or that the wave function was always just a description of a particular observer's knowledge rather than a picture of the world. In these views, there is no single, observer-independent reality to ask about in the first place, which fits uncomfortably well with the Wigner's friend results we just met. And the seventh answer says the collapse is real and physical and happens entirely on its own, with no observer of any kind. In these objective collapse models, the larger a system grows, the more likely it is to spontaneously settle into one definite state, so a particle can hover in superposition for ages. But a cat collapses almost instantly, all by itself, no looking required. What makes this family special is that it is the only one that predicts tiny, measurable differences from standard quantum mechanics, which means it is genuinely testable, and physicists are searching right now for the faint signatures it would leave. Look at that menu and notice the thing that should astonish you most. With the single exception of the objective collapse models, every one of these answers makes exactly the same experimental predictions. Run any experiment you like, and they all forecast the identical result. This means that, as of tonight, the choice between them is not something an experiment has settled. It is philosophy of physics, not settled science. The same flawless mathematics, the same perfect predictions, support a half-dozen completely incompatible stories about whether the world is there when you stop looking, and nobody has been able to rule the serious ones out. The equation works. What it means, we genuinely do not know. Now, I owe you a word about the question printed on the way into tonight, the one that asked whether reality might be a projection. It sounds like pure mysticism, and in its loosest form it is. But there is a thread of serious physics underneath it, and it deserves an honest answer rather than a dismissal. Beginning in the 1990s, physicists including Gerard Hooft and Leonard Susskind developed what is called the holographic principle. Studying the strange behavior of information at the edges of black holes, they were led to a startling suggestion. The full three-dimensional contents of a region of space might be completely described by information living on its two-dimensional boundary the way a flat hologram on a card can store a full three-dimensional image. In 1997, Juan Maldacena found a precise mathematical example in which a universe with gravity inside it is exactly equivalent to a simpler theory living on its lower dimensional edge, with no gravity at all. The two descriptions contain identical information. In a careful, mathematical sense, the inside really can be read as a projection of the boundary. So, is reality a projection? In the mystical sense, the sense where your mind renders the world on demand, and nothing exists until you imagine it, no. The physics gives no support to that at all. But in the precise sense, the sense in which the three-dimensional world you move through might be encoded on a distant, lower-dimensional surface, the honest answer is that some of our best physics takes the possibility seriously. It is not about a mind painting the world. It is about information and geometry, about the surprising idea that depth itself might be a kind of readout of something flatter and more fundamental. The cousin of this idea, the simulation hypothesis, the notion that we live in some grand computation that only renders what is observed, is philosophically entertaining and lines up suspiciously well with the observer effect, but it makes no confirmed prediction and remains a story rather than a science. And now, with all of that laid out, let us return to Einstein walking home in the evening, asking his friend whether he truly believed the moon is not there when no one is looking at it. To Einstein, the answer was so obvious it was almost an insult to ask. Of course, the moon is there, and tonight we can finally say what has become of his question. The experiments have not vindicated him. They have not given us back the simple, solid moon that exists in the dark exactly as it does in daylight, with definite properties waiting whether or not anyone looks. They have taken that moon away. What they have handed us instead is a question that has only grown heavier with every answer. A century of the finest experiments ever built has not closed Einstein's question. It has sharpened it into the most profound open wound in all of physics. Is the moon there when nobody looks? We still cannot tell you. We can only tell you that the easy yes is gone. The phrase we started with has changed too, hasn't it? What happens when no one looks? When we began, it sounded almost like a child's question, the kind you ask about the refrigerator light, a little spooky and easily answered. Now you have followed it all the way down. Now you know that the same words name the single thing the smartest people alive cannot resolve, the place where our most successful theory falls silent, the seam where reality itself refuses to commit. The words have not changed. Everything underneath them has. And the last thing I asked you to carry, all the way back near the beginning, was a small phrase. Looking is not the same as seeing. You can let it go now, because the journey has redefined it for you. Looking, the kind that makes the world definite, turned out to have nothing to do with eyes or minds at all. It is the touch of a photon, the collision of a molecule, the universe taking note of itself in the dark. Seeing, the conscious experience, the thing you are doing right now, sits on top of all that as a late and gentle arrival, important to us, but not, it seems, important to the world. The world was making itself definite long before anyone was here to see, and it will keep doing so long after. There is one more thing, and it is the closest the mystery ever comes to you. Whatever you are using to receive these words right now, a phone, a screen, a small, bright rectangle held in your hand or resting nearby, is built, at its core, from the very strangeness we have spent these 2 hours circling. The chips inside it work because electrons behave as waves, because they slip through barriers they should not be able to cross, because matter genuinely holds several possibilities at once. Every photograph it has ever shown you, every word on its screen, depends on the same superposition that, the theory says, may have no single definite state until something interacts with it. The mystery is not far away in a laboratory in Vienna or Delft. It is not out at the edge of a black hole. It is in your hand. You are holding it. You are using the unanswered question to read about the unanswered question, and no one alive can tell you for certain that these words were definite before you looked. So let the certainty go, just for tonight. Not because the world is frightening, but because it is stranger and more open than the solid, finished thing we were all promised as children. Maybe the universe is there in full when you close your eyes, watched into being by its own endless light. Maybe it waits, in some way we will never quite picture, holding its possibilities until the world forces a choice. Maybe every possibility is happening at once, and you are riding a single thread through a structure too large to ever see. We do not know which of these is true. That is not a failure to be embarrassed about. It is the honest edge of human knowledge, and there is a strange peace in resting against it. The moon is hanging over you right now, whether or not you are looking, or it is waiting, or it is everywhere at once. And as you drift off tonight, somewhere out past the window, the universe goes on quietly measuring itself, deciding what is real in every corner of the dark, asking nothing of you, needing no one to watch. It was doing it long before you arrived. It will be doing it long after. And the most wondrous part of all is that, for a little while, here in the middle of something this strange and this old, you get to wonder about it at all.